Many thanks for your introduction. Okay, I have decided for this title, and this is the outline of my presentation of today. I will give you first an overview of our company. Then I will present the software line that we have and how it can be used in industrial application, considering CFD, FEA, and multiphysics application as well. Let's first give an introduction. We are a small company. We are based in Italy. And our main focus is mesh morphing using radial basis function. About this technology, we have a very strong expertise in using radial basis functions, and we have also a quite good experience in creating vertical solution for a complex industrial workflow that are built on the top of this technology. Our products are currently available on the market as an add-on for the CFD solver ANSYS Fluent. We have also a standalone version, and the new product is an ANSYS ACT extension. I will give you a description in a few seconds. We were born in 2008 in F1, in a Formula 1 project. So the technology was driven by the industry to achieve the performance required for one of the challenge that they got at that time. It was indeed a good project, so we decided at the end of the project to enter business. So the software was launched in 2009. Here I have a short list of milestones of our brief story. The product was launched in 2009, presented at an automotive event where we were awarded as the most innovative approach using simulation methods. I'm proud of this. Since 2011, we started to cooperate with strictly with the University of Rome. This is one of the reasons I am involved. We are involved in Fortissimo as well. Since 2012, we are OEM partner of ANSYS, so the Fluent add-on currently is in the portfolio of ANSYS products. We are currently supporting 3 European projects. Since 2013, we started also a partnership with EngineSoft. So we are growing step by step. And here I have prepared this slide about our commitment in the creation of a full automated optimization workflow. This is something that is going on in the European FP7 RBF Morph project that is currently in the middle of the 3 years. And this is what we are doing more recently in our Fortissimo experiment that we are supporting that has been introduced yesterday. So let's summarize all of this stuff in this knowledge galaxy. We are strongly interconnected with academia and also scientific dissemination. So you can see we are active in praise. We are supporting many schools. We are active with cooperation, ANSYS, EngineSoft, the university, and indeed many others. And we are active in European funded research. Let me now give you an overview of our software line, and let me shortly describe what this RBF Morph stands for. With RBF, we mean radial basis functions. That is a technology that is recognized as the best mathematical tool for mesh morphing. This is not by us, but by the scientific community, of course. One of the problems of the radial basis function, it's very difficult to play with large data set, and we can do it quite well. the main benefit of using radial basis function is that the method is meshless. So the problem is not dependent on the mesh itself. And basically, as you can see in the image, you have a bike. We want to move the head of the driver. We can put a cloud of points, and we can prescribe a vector to each of these points. It's very easy. So what will going on is that the field of deformation will be exactly as we give at the points, and we will gently deform the remaining points. So this is an excellent tool to deform the mesh to accommodate new shapes. To make it more clear with an example, let's say that we want to move up one point on the top of this cube. We can put steady points on the boundary, one moving point in the middle, and we can deform this surface like this with a linear RBF, or like this with a fourth order RBF. Okay, so we use RBF to control surface, but this surface control can then be used in a more complex. You know that the number of points is growing. Now we are more than 1,000. So we can control the surface with a given shape, and we can put this in a box to limit the action with a 0, and so transfer this surface result on the volume. The cube in this example is immersed in a wind tunnel, and we want to not move the inside but the outside of the cube. These two make understand what's going on with radial basis function mesh morphing. This technology today is available indeed as an HPC radial basis function library that is the heart of all of our software line, and is deployed in 3 different solutions. The one that is used in our experiment Fortissimo is the ANSYS Fluent add-on. We have also a standalone version that is the basis of the optimization platform of our RBF Forareo platform, and I have already envisioned it yesterday that we could consider a strong integration between these activities. I mean, the RBF Forareo platform can be tested on the Fortissimo platform as well. And the last product that has been launched recently is the ACT module for ANSYS Mechanical. That is an extension that works inside the Workbench platform of ANSYS that enable this mesh morphing parametric. So about the Fluent add-on, it's a software that is integrated inside Fluent and inside also the adjoint solver of Fluent. It works in parallel. It can manage any kind of mesh. It supports the redesign, and thanks to the radial basis function technology, allowed to get a very high precision. The standalone implements the same technology, but it can be coupled with many solvers. Currently, we support OpenFOAM, CFD++, ELSA, NumECA, SU2, and many, many other formats. Let me go ahead. This is an overview of the ACT. In the ACT, the graphical user interface stays in the tree directly. The user can set up the problem, and according to the standard of Workbench, can enable parameters wherever you want to have automatic optimization that can be steered inside Workbench. So, why we use mesh morphing? First, this image allows to explain. Usually, workflow requires a geometry, a meshing stage, and then a solving stage. The geometry processing, the featuring, and meshing could be a costly part of the process. Using mesh morphing, we do it once. All the other variation can be quickly obtained by morphing and in a full automated fashion. So we can have automated optimization workflow in which we reshape the components, and we can drive this optimization with many tools. For instance, DX, ModFrontier, Dakota, MATLAB, custom application scripts, whatever you want. Our expertise is to provide shape parameters. It's up to the end user to decide the strategy. Some figures about performances. We can play with, let's say, from small, medium-sized meshes to quite large one. Here you can see some figures. we range from the 14 million mesh of Piaggio Aereo to the 50 million automotive of Volvo, to the 100 million that is motorsport of Dallara. But in any case, of course, you change the APC environment, but you can see that the mesh morphing, so the update of a new mesh, is a matter just of minutes. So the technology is really very, very fast. We act directly on the model ready to go for calculation. So all the setup stuff is conducted directly on the mesh. And this is very good because we can reshape something easily on the basis of result that we see without redoing the entire workflow. And what is important is that at the end, what we get, it will be just a mesh, of course, not a geometry. We have tools to back this into a CAD system. That is how to get back the result. So here I have an example of how this technology is enabled in HPC. Each column is one application. You can see the size is changing in the first yellow row. The number of design variation explored in the full optimization workflow is reported in the second row highlighted in yellow. And the runtime of the overall optimization workflow, that is what we want, is summarized in the third row. For instance, the 50-50-50 case, that was a project in which we worked together with Intel, Volvo, and ANSYS. You can see that you can do 50 design points with a 50 million cells mesh in 50 hours. That was the target of the method. Let me go ahead and show you some of the applications that can be phased with this technology and that can potentially be coped using what we are going to offer in Fortissimo platform. Yesterday, I have presented our experiment that is about internal flow for automotive applications. But of course, once you have in the cloud this technology, you can face many, many applications using this approach. This is motorbike. In this case, the target of the optimization is not the helmet, but the windshield. So this is a comfort analysis. We want to understand how to adjust the deflector, changing the sides, so the height of the driver, the driving position for different conditions. You can notice how this is full automated, are about 50 design points. Everything is automatic. The mesh is just one, and all the optimization are controlled by the mesh morphing. You can see how large is the impact on the mesh, on the structure of the wake. This is another application about sails. So the sails angle are made parametric, so you can tweak the parameters. This is an example in which mesh morphing is used to not reshape but for setup optimization. This is an example with Piaggio Aereo Industries. So this is the P1XX geometry. And in this example, we are changing the sweep angles. This is an exhaust system. You can see here how reshaping the exhaust system, you can achieve a very good solution with respect to the original one, in which the structure of the flow is very disturbed by the shape of the runners. And here I have a couple of automotive examples. This one is with Myra. This is an experimental shape, this Ghostbusters shaped car. It's very simple, but is a concept for study. And with this expertise and knowledge, we conducted the optimization of the XC60 Volvo. We reduced, this is the example of the 50-50. We reduced the drag by 5% in this application. Here I have a few examples of the ACT extensions, so about finite element analysis. This is the optimization of a connecting road. I go quickly. We get a 7% reduction in weight, keeping the same performances. This is a BGA solder joint study, and in this case, reshaping the bolts, we get a reduction of 20% in stress peak, like shown in this picture. And here I have another example. It's a wheel rim optimization. We have a complex calculation scenario that mimic the test that is used to validate the rim experimentally. And with this, we go from a baseline to an optimal shape, reducing about 8% the weight of the rim. And I have also some example showing how this radial basis function technology and mesh morphing technology can be used for multiphysics application. This is a motorsport application with the LARA. This is an aeroelastic analysis of the front wing using a modal superposition. This is an example of using a robust design and a joint together in an optimization of a Formula 1 front end on the Monza circuit. So many simulations are run using different steering conditions and different flow conditions representing points on the track. And all the optimization is conducted together to minimize the lap time. That is what we want in racing. This is another example of multiphysics. In this case, we use mesh morphing to account for snow accretion on high-speed train. So there are models that allow to understand how we collect snow on surfaces. What is difficult is to reshape the component to account of this snow layer. And we can do it with the radial basis function. And we can do it also for ice accretion, like in this example that is from our RBF Forareo project, in which we demonstrate how we can use the technology to simulate the accretion of ice on an aircraft wing. And I switch to the conclusion. I hope to stay in the time. I think so. In my presentation, I gave an overview of our mesh morphing technology and highlighting the key benefits. The main reason why we do this mesh morphing is that because we want to have directly the model ready to go for calculation parametric with respect to shape. We have demonstrated this with some applications, so I think it's better to say thank you for your attention and conclude my presentation. And so we can start the discussion. Okay.